Yeah, so very good evening, guys. So welcome to today's webinar. So just to give you an insight again, so today's webinar is about structure analysis. We'll be looking into a lot more on the same topic throughout the webinar. So in a short while, I'll be sharing my screen. So please to let me know when you can see my screen. Hope my screen is visible.
Yes, we are able to see your screen.
Okay, great. Thanks. All right. So yeah, so let me quickly jump to the first page. Yeah. So again, so we'll basically start with the overview of all this stuff, and then we'll deep dive into the topics. So first question, whenever any engineer who is basically there, the first and foremost question that comes to your mind is, okay, how are new products developed, right? So basically, if you talk about products, so any product that is going to be there in the market, or it is going to be manufactured, or it is going to be sold in the market, there will always be a need for all the invention. Okay, like for example, if I talk about headsets, right, or the buds, right, so there is always a need for wireless communication. There is always a need for a technology where you can basically listen to music, you can basically talk to someone over a call, right, or at the same time, you have a lot of features in that. For example, you have kind of volume features, you have kind of uh, you know changing features, so attending calls, ending calls, right, so waterproof, uh, mm, resistance. So all these things are all the features, the need for a particular product. And similarly, if you talk about cars, or bikes or trains or buses, every product that you see in the market will definitely have a need, and this need is basically satisfied by the product, right? So what are the major things that you typically see when you buy a product? Let's say we are going to buy an, or you or me are going to buy a automobile. So when we buy an automobile, or let's say a car, there are some things that we look at. For example, we look at how comfortable it is, right? So what is the mileage that my component is, or my car is giving, right? So I'll look at how frequently I'll have to look at the maintenance of the product, right? How safe my automotive component is, etc. So there are a lot of things that you basically look at, right? Now, corresponding to all these things, we will basically look at multiple products, and based on these multiple products, we'll choose what is of our best interest and we'll buy it. Similarly, any component that is being designed or manufactured is considered based on all these parameters. Okay, so before a product is launched, so we'll just look at the what are the different stages in development, right? So how do you build a safe product? So the first thing is the development stages, and this development stage is what is called as product development lifecycle, PDLC, is what is commonly known. Okay, so we have different phases, like we have close to 8 different phases in general, starting from market research, brainstorming, concept development, product development and detailing, simulation, physical testing, manufacturing, marketing, etc. We'll go through each of these topics one by one. Okay, so coming back to again the first question, why do I need a product? So this is where, when I'm going to design or manufacture a product, the first thing I'll do is market research. I'll understand the geography, I'll understand the demography, right? Okay, so who are going to use my product? So what is the lifestyle? What is the family setup? Right? So how's the climate? I look into all these parameters, all the market analysis, where is the need? So it's all about uh, you see demand and supply, right? So where is my demand? How am I going to supply it? How am I going to look at the need? So all these things I'll basically understand, and then a group of people will basically sit together and they'll do something just called as brainstorming. So brainstorming is a concept where people with like-minded people sit together and discuss on the market analysis that is being done to develop a product. So wherever there is a need, wherever there is a problem, people will sit together and identify a solution for the problem. And this, solution usually comes with, in the form of a product. Right now, once this is done, then is where you'll have the concept development, where the initial sketching part is done. So to meet the current requirements, okay, to ensure that the customer is satisfied with the product, will and also at the same time, not only customer satisfaction is important, so it is also a key parameter to think about, okay, what other components are there in the market and how is your product going to compete with similar products in the market. So this is where you develop concepts. So you do sketching, right? So you do all these things like you can see in this image, right? So if there's a automotive car that is going to be designed, the first thing that they do is they do a hand sketching, freehand sketching, right? Once they do a freehand sketching and basically they develop, then they go on to the next phase, which is product development and detailing, where whatever concept you have, you will convert that into a virtual product and you'll add more details, right? So this way you'll be able to have a real life experience on how the component is going to look in a simulation environment before the component is basically manufactured. Right. So this is where we provide all the detailings. Okay, well, let's say if I talk about an automobile, so I'll be working on the BAW parts, I'll be working on the interior plastic parts, I'll be working on the powertrain, the electrical components, all these things. Right. So this entire product, once it is developed, then I'll be doing simulations. Now, what are simulations? So basically, when I design or you see develop and detail a component, I'll not know if the component is good enough or not. Okay, so in order for me to find out, I'll have to do simulation. I will look at what a simulation shortly, but then so we do design optimization, meaning develop the best product which is going to be fit for the market. Okay, and when you do simulations, there is no need for a prototype in the sense a physical model where you need to test. Similarly, we'll look at durability, we'll look at life cycle, we'll look at quality, we'll look at the cost, affordability, right? So all these things will basically plan, and post which we'll do physical testing. So we'll do a prototype. So instead of developing 300, 400 models and then doing, you know, real life tests and then coming up with a new product, people will do virtual testing and they'll come up with an optimized solution. And from there, they'll manufacture a component and they'll do all kind of testing, physical testing. Like for example, you can see here, when you develop a car, some tests involve doing crash tests, frontal crash, side crash, roof crash. You see a lot of different types of crash tests, right? And all these crash tests are basically done based on a certain set of standards, right? So once this is done again and verified with this physical, so you basically do physical test and you do simulations. So you compare both these results and validate the results. Once they are validated, the next thing is where you do manufacturing. And once it is manufactured on a large scale, you make it available to the customer on road. And in order to sell this product, you'll do marketing, right? So you'll pick up all the unique selling points of your product. So why is this product better than the other products in the market, right? So all these things to increase competitiveness. So you'll do, and you'll talk about all the functionality, and then finally you'll deliver it to the market, right? Once this is delivered to the market, again you will collect feedback and it will go back to brainstorming stage where whatever problems are there that are faced by the customer, they'll be coming back to the brainstorming stage, and then a new product again will be, or a counter product will be developed again, right? So this is the general overview of the product development life cycle of a particular component. Right, now the question is again, so we looked at all these things. Now we looked at all these points and stuff. Now the question again is, how do I build if I'm going to build a car? So since we are all mostly engineers, the primary thing that we'll look at in terms of automotive field is, okay, I'm going to build a car. I've decided that I'm going to build a car, but then how do I build a safe car, right? So how do I make sure that if my car goes into an accident, right, or if any such sort of natural phenomenon or any phenomenon that happens, how do I make sure that whoever is using that particular product is safe? Okay, this is where again question comes. Okay, what happens during a car accident? How do I build safer cars? How do the industry solve this problem of building safer cars? You're getting my point, right? So this is where FEA comes into picture. Right. Now, what is FEA? FEA is basically a method where you solve a physical model. Okay, you have a physical model in real life. Now you solve this physical model by a mathematical numerical technique. Okay, and what you do is basically you discretize, you basically do net generation of the model into nodes and elements, and you get approximate results. Like as you can see here, this is a particular product that you can see here, right? A spanner, right? Now, if I'm going to basically do an FEA simulation or an analysis on this particular spanner, the first thing I'll do is discretize my model, meaning I'll generate mesh-like structure, and with this I'll apply all the boundary conditions, meaning, okay, where my forces are going to be there, how my component is going to react. I'll do all these kind of setups and I'll get the results. Now, this colored structure, as you can see, is the contours. We call this as contour results, simulation results, right? And the results that we get, we analyze them and see whether this is going to withstand this particular amount of loads or not. And accordingly, we'll decide whether to go for manufacturing or to change material or do some optimization. Right. So just to repeat, FEA is basically a method where you solve a physical model using a numerical technique. So use mathematical modeling. How you discretize your model into elements and nodes, and the results you get is approximate. Okay, how approximate the result is basically depends on the mesh you deploy. Okay, so the more finer your meshes or more smaller the meshes, the better is the accuracy of the approximate results that you get. Okay, yeah. So then again, so there are different steps in FEA. Right, so FEA, like for example, you have physics, you have pre-processing, solution, and post-processing. Okay, so everyone here knows a crane, right? So you might have seen this particular crane in the construction buildings, right? Now, if I want to talk about an analysis on this particular crane, right? So what's the first thing I'll do? The first thing I'll do is understand the problem. So understand the problem in the sense I'll have to basically figure out why I want to do a particular testing or a simulation or or an analysis on the component in the first place. Okay, once I figure that out, then I'll understand the problem. Okay, how is the component? So basically, my crane will have a counterweight on one side. Okay, let's say I basically draw some kind of sort so that you can understand. Let's say this is my crane, right? So here I'll have a counterweight, and here I'll have a rope. And this particular rope, I'm just drawing a free body diagram so that you can understand. Right, and here you'll have a rope, and this rope is going to lift a weight. Right, so here you're going to have counterweights. This side, your body is going to be fixed, and this rope wire is you should be able to it should be able to move up and down. And here you will have a pulley that will basically help your component move left and right. And here you will have a motor that will help your component rotate about a particular axis. So this movement or rotation is what is all about the degree of freedom. Like for example, this is translation. Uh, this is translation along a particular, let's say this is X and this is Y. Right, so you will have translation along X, translation along Y, and you'll have rotation about X. Right, so rotation about X again, rotation about a particular axis. Right, it depends. Right, so this analysis, and again, what is the material that my component is made of? Right, all these things is majorly what concerns physics. Okay, now followed by that, you'll do pre-processing. So pre-processing is where you do meshing of the component. Okay, you have a physical model, basically a design that comes from the design engineer, and this particular component that is designed, you will import into certain softwares. We'll discuss about the different softwares used later stage, but then you will import it, and then you will do the model setup and the pre-processing part. So model setup is where you assign materials, you assign properties to the components, right, in the design, and then you basically set up all the boundary conditions. Like, okay, this is where my fixed support are going to be. This is where my weight is going to be. This is what is the material of this particular rope. This is how my rope is going to move. This is my crane is going to move. All these things I'll basically set up, and then I'll solve. Now, what would I solve for? I'll solve for stresses, I'll solve for strains, I'll solve for all these parameters that I need to find out. Okay, simple thing. Why am I doing simulation? I'm doing simulation to find out whether my component is going to be safe or not safe. Is it going to break or not break for this particular load? So I'll find out all these things, and then I'll post process results, meaning I'll analyze whatever results I've got. I'll plot graphs, I'll plot charts. Okay, I'll then document all the results and then evaluate or validate my results. So this is the major steps in FEA. Okay, so again, the same thing is what is discussed here. So pre-processing. In pre-processing, you discretize your component, meaning let's say you have a sphere ball, another example. Okay, first process, which is pre-processing, is all about converting your ball and this plate into mesh-like structure. As you can see here, this is an very good example of a mesh. Now, each of these square-like structures you can see is what is called as an element, and each of the element is basically connected by using the nodes. Okay, so you'll have nodes, and all these nodes, if you connect, they'll form an element, and each elements are connected to another element. Let's say one element is connected to another element through common nodes. Okay, now to do this discretization or meshing, we have some tools. These tools are what are called as pre-processing tools. And Hypermesh, Hypermesh is a product by Altair, ANSA is a product by Beta CAE Systems. So these are some products that are used to do what? That are used to mesh or pre-process my component. Right. Once I pre-process, I have solving. Okay, solving is nothing but running the simulation after I apply all the boundary conditions. Okay, so this is where you have a stage where you set up the case for the model and to a very similar real-time application, and then you solve it. Okay, a very good example. Let's say I have a button in the keyboard. Right now, what is going to be the button in the keyboard? So basically, my keyboard button should not be able to rotate, right? Or it should not be able to move left or top. It should be only able to move up and down. You're getting my point, right? So this is going to be my boundary condition. I'll set that. Another boundary condition is the force that is going to be applied on this particular button. Right now, once I do this, what will I do is I'll basically find out, okay, so after how many times of pressing this particular button, my button is going to fail. So as you can see here is an example of how the solving is done. So this is a solver, which is a radio solver, and all you can see is that okay, there are some time running, there are some errors showing up, there are some mass showing up. All these things are what are basically seen here. And you have another solver, a lot of different solvers. You have radios, you have LSTN, you have ANSYS, you have so many other different solvers. Okay, this is what is solving. And then you have post-processing. So in post-processing, once you solve, as you can see here, you can see one mesh's contour plot here, right? So which is stress. So you can see different colors that are showing up. Okay, I'll basically see what these colors represent, what are the values corresponding to these particular colors. I'll plot all these graphs of all different energies and basically find out whether this is good or bad. Once I find out whether this is good or bad, I can basically decide whether to proceed or to go back and do a simulation again. Again, tools that are used are Hypermesh, Hyperview, Hypergraph, not Hypermesh, Hyperview, Hypergraph 2D, and MetaPost. So these are all some tools that are used. Okay. Now, we talked about FEA now. So then we have another concept or a technical term, that is CAE. Okay, CAE stands for computer-aided engineering. Now, what is computer-aided engineering? So basically, computer-aided engineering is an engineering process that allows a person to perform tests and simulations on the product's physical properties without needing prototype. Meaning, I don't have to basically do analysis on a physical component. Instead, I can work on something virtually, right? Without needing a physical prototype. So this is what is CAE, right? Using help of systems or computers to aid in engineering in a simulation world or a non-physical environment, right? There are different techniques in CAE. You have 8 different techniques. You have non-linear, static, linear, non-linear, linear, static, dynamic, buckling, thermal, fatigue, CFD, NVH, all these different terminologies. So we don't have to deep dive into each of these things. Okay, but just now, for now, understand that there are multiple different techniques that are present. Okay, now coming back to the part again. So how do you solve an engineering problem in the first place? So we saw a lot of things, right? So we saw all these FEA techniques and stuff. But generally, if you have a problem during brainstorming, they think of, okay, so we'll have to solve the problem using any of one of these things: relative testing, analytical method, and numerical testing. Now, what is relative testing? Relative testing is all about physical testing. Okay, doing experiments in real life. Like for example, you have an electric scooter. If you have an electric scooter and you want to understand, okay, so how much force my foot pedal is going to withstand. So what I'll do, I'll take 100 kg weight and I'll put it on this particular footrest, and then I'll understand whether my scooter is going to brake or not brake. Right. So this method is very costly and time consuming. Why is it costly and time consuming? If I want to do an analysis, I have to manufacture this entire product once and then do a testing. In case it breaks and I want to change a different material, so I'll have to change, again manufacture, again test to understand if that particular new material that I'm selecting is going to break or not break. So similarly, the cycle keeps repeating until I come up with an optimized plan. Right. So that's why it is very costly and time consuming. The next thing is you have your analytical method. So what is analytical method? So you typically have textbook formulas, you do mathematical calculations, you basically use all these things and then find out, okay, how much is the displacement or deformation, right? Whether my component is breaking or not breaking, all these kind of stuff we'll do. Okay, this analytical method is very limited to simpler problems. You cannot do complex problems. If you take a car, you cannot do hand calculations or mathematical calculations on a car. So that's exactly why we have softwares or solvers to run those things. Okay, so again, this is analytical method. One advantage in analytical method is you get very accurate results. Disadvantages that you can have parallax errors or human errors, and you can basically have, you cannot basically use this component in terms of complex models. Right? So this is analytical method. Then you have numerical method. So numerical method is what we do in simulation environment like CAE or FEA, where you do virtual testing on a CAD model. You find out use numerical solutions to obtain different results. And using this, you have way reduced costs and time is also less comparing to other two methods. Okay, so these are some examples of simulations, right? So as you can see, this is a particular buckle clip simulation that is being done, right? So this is a spur gear simulation that is being done, right? So these are some MBD simulations that are being done. So this is a frontal crash simulation that is being done on a particular truck. As you can see, you have a human dummy, you have this airbag that is being open, and you can see your front hood or a bonnet that is being crumbling, right? So you have your engine components, your tires, all these things. You have your, you see your powertrain, right? So based on this crash, what's happening? So where is the stress produced? What all components are failing? How much is the injury to my passenger sitting inside? All these kind of things we'll basically do, right? Now physical testing versus simulation differences. Cost. Physical testing is high cost, simulation is low cost. Okay, high cost in the sense, so let's say if I'm going to do a testing on a car, typically I'll need 200 to 300 cars on an average to come up with the best possible material and design and structure for my car on an average. Okay, but when I talk about simulation, I'll only need good computers and softwares, and the cost is very less when compared to physical testing, because I don't need 300 cars. All I need is a good computer and a software, and I can do multiple iterations. I can do this simulation or the testing, the virtual testing 200 to 300 times without the need for manufacturing and assembly, right? Hence low cost. Time consuming again. So for each car you basically test, or each time you test, you'll have to manufacture it, and manufacturing again requires more time, right? Similarly, when you talk about simulation, you don't need, okay, if I, let's say I want to change a material for a component, I don't have to find a material, raw material, and then process it and manufacture it. All I have to do is do some values changes. Let's say for Young's modulus density, I'll change Poisson's ratio and some other material properties I'll change, and then my material will change to a different material, right? Similarly, in physical testing, there's a lot of wastage, and in simulation, you don't have any wastage at all. Physical testing, no waste. More waste. Simulation, less waste, as the car is not yet manufactured. Okay. Now, again, so physical versus simulation. So basically, this helps us understand uh, if the physical response. So how we need to, how we have done design. Okay, so again, we are talking about physical and simulation and stuff. Right now, there might be a lot of questions in your mind that, okay, so you're telling me that physical testing is very, very costly. Simulation is what mostly everyone prefer. So again, you'll see question on, okay, why do they, only go with simulation, or why do they need to only go with simulation? Why don't, uh, do they not do physical testing at all in the first place? Okay, they do physical testing, but they don't do for multiple iterations. So they basically do simulation first for different iterations. And once they get a finalized result or a finalized product, this product they'll manufacture once or twice, and then they'll do physical testing. Okay, so again, as you can see here, this is a side crash simulation that is being done in real life after full optimization, and uh, a virtual test that is being done, right? So in both the cases, at a particular velocity, they will check what's happening. So this is two are different cars, so you'll not be able to compare actually. But then if you talk about same car design, I think you'll be able to understand so what's happening in detail. Right. So this is the different methods of testing and validation. Physical testing, computer testing. They'll compare both the results and they'll find out whether both are same or not. So the maximum deflection that one can have is 5%. If let's say I get deformation results as let's say 100 mm, okay, what I can have here is plus or minus 5% of 100 mm, meaning 95 to 105 mm is the maximum limit I can have during a physical testing, or vice versa. Right. So this is thing. Now talking about simulation process. Okay, so when I talk about simulation process, so typically I'll have a CAD team, meaning a design team that will design my product, and then the product will come to a simulation team. Once it comes to a simulation team, the simulation team will pre-process it using tools such as Hypermesh, and for this, engineers will be required. Now, this engineering role will be called as a meshing engineer role, right? And then you have a solver. Once pre-processing is done, you'll have solver, and then post-processing. So solvers example, ANSYS Workbench, Radios, LS China. Post-processing examples, Hyperview, Hypergraph, LS pre-post. So this job role is simulation engineer role. Now, after all these testing, if the product is good and yes, they'll proceed to manufacturing. If it is no, then they'll do some design improvements. They'll suggest some, not do, they'll suggest some design improvements. And these design improvements will go to CAD team. And then once they reprocess all the design, the same cycle will repeat again until this becomes yes and it is approved for manufacturing. Okay. Yeah. So job roles and hierarchies. So this is where a pre-processing engineer is. And then the next level is solving engineer. And then the next level is post-processing or simulation engineer. Okay. Now we talked about simulation, sir. So what exactly is simulation? Okay. So the definition for simulation is very simple. Okay. Understanding the behavior of a model using using physics, not physical, using physics, and trying to analyze the problem virtually. Two keywords are there: understanding the behavior. Keywords are marked in red color. Understanding the behavior of a particular model using physics, and analyze the problem how? Virtually. So if you do this, this is simulation. In simulation, you don't need any prototypes. And then you might have heard a common terminology, which is analysis. So what is analysis? Right. Investigation, which is being done on what, how, why things happen during a simulation. Right. So that is analysis. For example, if let's say I'm doing the simulation, right? So this is a skateboard. Now, if I apply a force on the skateboard, and what is happening is, let's say my particular skateboard is basically deforming or getting damaged. Okay, analyzing what happened, how it happened, and why it happened during the simulation is what is analysis. Okay, typically studying the model to enhance its serviceability. So this is also analysis. Okay, now the question is again, why do we need a simulation? We already saw why we need simulation. The answer is very simple. We need to virtually evaluate the behavior of a model, and to reduce cost and reduce physical testing, we need a simulation. Right. So this is an example of a simulation that is being done. Okay, this is a simulation that is done by beta CAE simulation systems. Okay. Now, as you can see here, you may not be able to hear the video, but then what is being done is the Volvo car is taken, and they are running the car at 35 miles per hour. And what they are doing is they're doing a straight crash, frontal crash. Okay, so this is the interior. Now they are running at 35 miles per hour or 56 kilometers per hour. Right, and they are doing a crash. You can see on the right side, they've done a simulation. On the left side, you have a real-time testing. Now you see the difference. What's the difference? Very small, no difference at all. Okay, whatever is happening in the simulation, same exact thing is happening in the real test. As you can see, exactly from how the dummy is coming in contact with the airbag, to how the airbag is inflating, to what components are breaking and flying off, to everything. Right. So this is why people do simulation. And even the deformation cycle, where it is deforming, how it is deforming, even these stress wave propagations. So everything is almost same, right? So this is again a frontal crash simulation that is being repeated. So yeah, this is the top view of the simulation, right? As you can see. Yeah, so this is the bottom view of what is happening underneath the car. Right. So this is, you see how close the results are in the softwares and the physical test, right? So yeah, this is why we use simulations, right? Okay. Yeah. Let's stop this. And yeah, again, you're able to understand, right? So this is basically why we need simulation. So we'll need a process where we can virtually evaluate the behavior of the component and then do a physical test. And then we can typically compare and understand what's happening, right? The next part is again where to start. So now we talked about all these things, right? Okay, so simulation, analysis, and the need for analysis and everything. Okay, so let's say if I am going to pursue a career in CAE or FEA, where do I start? Okay, so there are software such as Altair, ANSYS, and etc. Okay, so the first and foremost thing, how a simulation is done is studying the CAD, meshing, assembly, then assigning materials, thickness, loads, and we solve it, we get results, and then we analyze results. Okay, now if I am going to be a person who is interested in doing a simulation or working on something, the first and foremost thing I'll have to learn is the skill to mesh. How do we do meshing on a component, right? So what tools I can use to do meshing? Tools such as hypermesh and answers what is used for meshing, right? So I'll basically be understanding or learning. I should learn how do I do meshing. I'll learn all the fundamentals. I'll learn subjects such as strength of materials, right? Finite element analysis, all the engineering behind the particular uh, car. I'll relate the subjects and I'll learn first, and then I'll learn about materials. I'll learn about all the uh, loading stuff, how different types of, what are the different types of loadings, how they are applied, right? All these things, how each material behaves. So I'll talk about all these things, followed by which I'll learn how do I solve it, how do I analyze all these results, and how do I correlate them with the real life simulation, real life testing that is being done, right? So real time application of simulation, as you can see, is you can see a blender or a particular simulation that is being done on a particular water. And any new product that you build will require simulation to check whether the product will survive the conditions or not. Like for example, cars, aircraft, smartphones, toothbrush, any component you take, you'll have to do virtual tests to understand whether your component is going to survive in the real life world or not. Okay, so these are some examples that are given here. Like as you can see, when you buy a shoe, people are basically trying to analyze, okay, where are all the stress points in the shoe. Okay, so when you wear a shoe and then when you press it on the ground, where is the maximum pressure, right? So where is the maximum deformation that is being there? How do I counter it? Similarly, talking about a toothbrush, similarly talking about an aircraft aerodynamics, external aerodynamic simulation, right? All these things are why primarily simulations are done, right? Now, the next question is, okay, so what a simulation engineer does in an industry. So simulation engineer is responsible for simulating the product behavior for the corresponding loading conditions that are given, right? So he should basically, after you do a simulation, you typically investigate whether the results that you're getting is logical. And if you are not getting it logical, basically you give feedback to the design team on, okay, how is it behaving and how is it expected to behave and what changes are actually required. Are the materials need to be changed, or the design in the fundamental itself is need to be changed, or what change is required, and accordingly give inputs to the design team so that they can remodify the design. Okay, again, as you can see here on the screen is an example of a drop test, phone drop test. Okay, now this is a very good example of with case and without case. So you all have these phone cases, right? Now if you see the phone cases, without case, when you drop your phone, you can see that the acceleration is quite not a uniform curve, right? It's a very random curve, and the amount of acceleration, as you can see, is very, very high. So it's somewhere close to 14,000, as you can see here. But when you have a case and when you drop it, a lot of force is being absorbed by your case, and then you are having damage to your phone, because of which you have a different curve. And similarly, the acceleration that is being produced is also again less, right? So as a simulation engineer, what I would do is I would basically do these kind of tests, and typically I'll understand, okay, what's happening with case, without case, what kind of case is best preferred, how do I evaluate it, all these things. Okay, now this is what is all about a simulation. Followed by this, we'll see how various systems work, right? Yeah, so just give me a minute. Yeah, we saw this. And then this is a very good video of mid-surfacing part, the meshing part and the mid-surfacing part. Let this video play again. This is your component. And as you can see from this component, you'll have a definite thickness, and you'll take the mid surface of this particular component and you'll mesh it. As you can see, this is a 2D quad mesh that is being deployed, and you'll assign thickness to this particular mesh in order to define or have the same look as how your component is. Right. So the FE model was visible on the left side, and the geometry, the design was visible on the right side. Okay. So again, if someone asks you what is meshing, meshing is a process where you convert your model into a finite structure, like a mesh structure, to do simulation on the component. Right. So as you can see, this is the thickened model. Right. So this is the parent, and this is the FE model that you can see. Okay. Similarly, you have this pre-processing again. Another example, helmet. Okay, this is a virtual helmet, as you can see, and this is the meshed helmet, as you can see. Right. Now here, what I have done here is basically I've taken this model and I've meshed it. I've assigned materials, and I'll be assigning loads. Okay, now as you can see here, this is the real helmet that you can see, and you'll also be able to see a virtual uh, set of the same thing. Okay, now this is a CAD model, the design of your helmet that is being done. Okay, so using software such as CATIA and etc. And then you have your meshed model. Now this meshed model is a very similar replica of how you have your CAD and your real stuff. And now this meshed model is basically taken for analysis. They do drop tests, they do integrity tests, right? So you have a visor, right? So what they'll do is they'll shoot particles on the visor to understand whether your visor is able to withstand that particular crash or not. Okay. Now the next question is, okay, so what will I be in the future if I basically learn all these things? Okay, there's a lot of scope for you if you take up this particular domain. Okay, you might probably become a meshing or a simulation engineer, where you'll be responsible for setting up the simulation, work on the simulation without errors, analyze all these results, and validate the results. Okay, now as you can see here again, there are some examples that are given. This is a pedestrian head impact simulation that is being done. So what happens when a car hits a particular pedestrian, and what is the injury that is happening to the pedestrian? So how much is the head injury? How much is the damage to my car? Right. So how safe the passenger is after the crash happens? All these kind of things is again what are example of simulations, and these are the kind of stuff that a simulation engineer will be responsible if he is going to become a CA engineer or a simulation engineer. Right. Again, you might do meshing, or you might do simulation, or you might do validation. Validation again is like, for example, let's say I have a virtual simulation and I have a real life simulation. I'll be comparing both these results, and typically I'll understand whether the results are same or not, and accordingly I'll be processing it. Right, as you can see here, these two this is a simulation that is being done by Honda on a Honda car, and this is the particular crash that happened, the frontal crash that happened. Right, as you can see, both are very, very close. right? Again, so how close your result is depends on how skilled your engineer is. Okay, similarly, you'll do again validation, right? So this you'll see, okay, so if let's say my frontal particular component deforms by let's say 100 I'll also understand whether it happened in the real life. So I'll be installing sensors and everything, and I'll be tracking all those things by plotting graphs and etc. Right. So a project engineer might look at the animation and result and conclude whether the product is safe or not according to the design and give feedback to the design team in case there are any improvements needed. That is what is going to be the role of a post-processing engineer. Okay. Now, what are the fundamentals that I'll need if I'm going to become a CA engineer or an FE engineer? Okay. So you'll have to have very good fundamentals in metallurgy, engineering graphics, strength of material basics, manufacturing concepts, theories of machines, and kinematics. Okay. These are the major subjects that you will have to be good at, or if not, at least be familiar with, so that you can become a good simulation engineer or a CA engineer, meshing engineer, or a FE engineer. Okay. Right. Again, so what are the softwares that an FA engineer will be using? So if I'm going to take up pre-processing, I'll be using software such as ANSA, Hypermesh, ANSYS Workbench, etc. For solving, LS10R Radius, ANSYS Workbench, and for post-processing, LS Pre-Prost, ANSYS Workbench, right, Meta, and etc. Right. So again, where will I be in the future? So if you want to take up a particular role as a FE engineer, you will have to be having a good understanding of strength of materials and finite element analysis. You will need strong theory, fundamentals in this, and then you'll need to understand the physics of the problem and know basics knowledge about meshing. How do you do meshing? What software is being used, and etc. Okay, where will you have the application if you go on to these things? So fundamentally, you have 14 different types of industry that you have in the market. Okay, you have automobile industry, aerospace industry, you have med tech, you have basically oil and gas industry, you have petroleum industry, right? So you have military and defense. You have so many 14 different types of industries. Now, anywhere where a simulation is being done, a structural simulation is being done, you can basically be a part of the particular simulation that is being done. Okay, if you basically have a good understanding of all these things. Okay, career wise, so as an entry level engineer, so you might get into as a GET role, a graduate engineering trainee, or a meshing or a CAD engineer, or if you have some experience, you might go in as a simulation engineer or a project engineer. Okay, now again, what are kind of the roles? So if I'm going to be doing pre-processing, I'll be using tools such as ANSA Hypermesh, and I'll get roles such as meshing engineer or CAE model. Talking about solving, solvers which that will be using ANSYS Workbench, Radius, LS10R. These are the most prominently commonly used softwares. Okay, now what will be the role? I'll be a CAE analyst or a simulation engineer. Talking about post-processing again, you'll have ANSYS Workbench, Hyperview, Hypergraph, LS Pre-Pros, etc. And what will be again be the role? The role will be kind of a CAE analyst or a simulation engineer. Okay. Now again, process flow. We already saw this, right? CAD flow, input simulation team, pre-processing, solving, post-processing. Now in each phase, we talked about all the different tools that are there, Hypermesh, ANSA, and etc. Okay. Now talking about the courses that are there. So like you have these courses, pre-processing for structure analysis using ANSA. You have Hypermesh course for FEA plastics and sheet metal applications. Talking about all these solvers, you have courses such as ANSYS Workbench course, crashworthiness course using Hypermesh and Radius, and LSTNA course. Right. Now coming to how you can categorize all these companies. So typically, all these kind of roles that you saw here are spread across different kinds of companies. These companies are categorized into 4 different sections: the OEM, original equipment manufacturers, the tier 1 companies, the tier 2 companies, and the tier 3 companies. When I talk about tier 1 companies, so OEMs etc. are examples: BMW, Audi, Honda, the original manufacturers of the components. So they are all OEMs. Okay. Then tier 1 companies are the companies that help in supplying of parts or working on simulations for OEMs. You have companies such as Segula, Scient, Explio, etc. Then you have tier 2 companies. Tier 2 companies are non-automotive grade parts. Like for example, if you want to manufacture small components such as bolts, such as belts, right? Such as all these small parts. to support tier 1 companies, then those are Magna, no, company examples, Magna, Yazaki, etc. Right. And then you have tier 3 companies. You also have service level companies. Okay, so these are companies that provide services, that provide materials, raw materials and semi-raw materials to tier 2, tier 1 companies. Okay, example 3M, BASF, etc. Okay, these are the company structure. Now, each of these companies would basically have their different openings, and they'll have different skill sets that they'll define, and they'll have different job roles, and you can get into such kind of job roles if you are qualified enough. And now, as a fresher, uh, if you're coming from a tier 2 college or a tier 1 college, you might probably get into any of these two sectors, tier 1 or tier 2 sectors. And once you have some experience, 3 to 5 years of experience, you can probably see if you can move into OEMs. If you're lucky enough, you might get if you're skilled enough, if you're lucky enough, if there are openings and you're you are at the right place at the right time, I think then you can easily also get into some of the OEMs as well. Okay, now there might be a lot of questions in mind. Okay, so if I'm interested, so where do I start? What will I be in the future? Who will assess me? When should I start learning? What should I learn? The answer for all these questions is Skill-Lync. Right, so what is Skill-Lync? Skill-Lync is a platform where you have industry expectations and you have engineering knowledge. We bridge the gap between these two things. Right, so this is where we provide a lot of kind of courses. Right, so you saw a lot of different kinds of courses, right? So you have different postgraduate programs and pre-graduate programs as well, where if you're a student or if you're a working professional and you are interested in switching jobs or interested in switching to this domain, we are the person who can help you with the best. So talking about all the different courses that are being provided, so what you can do is you can type in skill-lync.com and you'll have courses. If you talk about courses, you have courses such as, you see in FEA, you have courses such as the postgraduate program in CAE and etc. Right. So if you go inside this particular course, you'll be able to see so why you should enroll in this program. All the unique uh, points will be mentioned. And then you have courses syllabus. We saw ANSA course, right? Pre-processing for structure analysis using ANSA, hypermesh course, right? Then you have a refresher for fundamentals, strength of materials, FEA. You'll be learning all these things here. Then you have LSTNA course, right? Crash worthiness course. All these different kinds of courses where you'll be learning all the different things. For example, if you talk about ANSA, you'll typically be learning how the GUI works, what are the different tools that you can use. You'll be learning about all the different mid surfacing methods, the meshing, how do you do meshing, what are the quality criteria that I'll have to use when I'm meshing, right? So then I'll be typically working on different kinds of components. So if you see automobiles, right, so they'll generally be categorized as sheet metal parts and plastic parts. So sheet metal parts will mostly be of exterior parts, right, like the BIW, side door, back door, your roof, your hood, your floor panel, your shotguns, your rails, your pillars. All these things will be made of sheet metals. Similarly, if you see the interiors, like for example, your dashboard, your side door panel where you have those latch to open and close doors, right? Your handrests, your coin holders, all these things are plastics. Your B pillar covers, your roof, inside roof, all these things will be made of fabric and plastics. So how do you work on those kind of components, right? How do you work on solid big components, right? So how do you connect all these components, right? So all these techniques is what you'll be learning in this particular ANSA course. Similarly, if you talk about hypermesh course, you again will start with the fundamentals of FEA, followed by which you'll have the graphical user interface explanation of hypermesh, and then you'll learn about key geometric tools. Again, 1D meshing, you'll learn about mid surfacing, 2D meshing, quality criteria, right? So you'll be learning about advanced 2D meshing, then 3D meshing concepts, right? Then connections, batch meshing, morphing. You'll learn all these concepts in your hypermesh course. Similarly, you have LSTNA course, you have crash worthiness course, you have ANSYS workbench course, and all these courses. Now, if I talk about the projects that are there, if you see in ANSA, you'll be working on real life automotive components, like for example, your dashboard, your suspension assembly, right? So then when I talk about LSTNA, you have this head impact test, you have your birds like on an aircraft engine using cell elements. Then when I talk about crash, you'll do frontal crash analysis on a particular BMW car. You'll do side impact tests. You'll be doing roof crash tests, etc. Okay, again, when you talk about answers workbench course, you'll be having an independent projects. When I talk about hypermesh, you'll be having side door panel, floor panel. You'll be working on meshing, right? So all these different kinds of courses will have its own individual projects on an average. So these projects are the stuff that are going to help you showcase that okay, you have had enough skills, you have done some progress towards your coursework or your career, and this can basically get you jobs inside the industry. So on an average, you'll have 2 major projects in each of the courses, and you'll typically have 6 to 7 to 8 small projects in each of the courseworks. Those will be kind of challenges. Like for example, an answer course, you'll be working on small components such as your front hood. Front hood is not a small component, but then it's a very big component. But compared to the entire automotive car, it might be deemed as a small component, right? Similarly, you might work on plastic components such as your engine parts, your turbochargers, right? Your engine casings, etc. And then you'll work on projects. Same is applicable for each and every course. Right. Now, who are the companies that are basically hiring, or whoever is studying the courses? What are the different companies? These are different types of companies, right? So some of the common companies that are that people get placed are Cyient. We have Tata, Tata Autocom, Tata Elxsi, and Tata Technologies. You have then Actel and Mahindra, right? Tech Mahindra, right? So you have Ola Electric. So there are a lot of companies that people get placed in. Okay, so yeah, similarly, just like how you have postgraduate program in CAE, you also have other programs such as crash worthiness course, where you'll typically learn only about the crash worthiness parts, right? Like for example, if you look at the syllabus, okay, I think you'll start with the basics of crash worthiness, right? Followed by which you'll have sorry, basis of crash worthiness courses. You'll have different courses uh, where you'll be learning crash worthiness, you'll be learning LSNA, you'll be learning a lot of things, and you'll also have all these courses. I think this is a individual course. So you have postgraduate program in crash worthiness. Okay, let's say if you get into this, you have a postgraduate program in design for crash worthiness, right? So here again you have a lot of different courses. Like for example, you'll have your answer course, hypermesh course. These courses are common courses that you'll, no matter what, you'll require. Then you have automotive safety standards course, you have crash worthiness course, right? All these different kinds of courses that are provided. And once you basically complete all these courses, you'll also be provided with job assistantships. Okay, if you are eligible for this. Similarly, you will have projects. Right, so projects is the one thing that is going to help you get a job. Right, so yeah, again, so these are the different stuff that you can learn from in Skill-Lync, right? And yeah, so just to give an overview again, so this is how the job role is going to be. I mean, the roles are different. Roles are going to be meshing engineer roles, simulation engineer roles, and etc. And in case you are interested, so you can take up courses and learn. Okay, now talking about the questions, I think now it's time for Q&A. Okay, there are some questions in the chat box. Let me answer them. Okay, so a lot of questions are about certificates. So shortly, I'll be sharing you a link. And once you fill that link, in 2 weeks' time, you will be getting your certificates. Okay. So how do I connect with you? Okay. So there are some questions regarding SolidWorks. So SolidWorks and CATIA will not be sufficient for simulation and FE. Okay. Yogi, that's a good question. Okay, if you're there in the call. So SolidWorks and CATIA are design softwares. Okay, they are not sufficient for FEA. Sorry, for FEA, you have a different set of softwares, like for example, Hypermesh, ANSA, that answers radios, LSTNA, etc. Okay, so if you are a person who's interested in simulations, I think you'll have to start learning tools such as Hypermesh or ANSA or answers workbench and etc. Okay, and then you have all these feedback links and stuff. So I'll be sharing you a form now. Yeah, in the chat box. What you can do is you can fill this form, and once you fill this form, basically, so please do fill the form genuinely. You will be getting your certificates in 2 weeks to 3 weeks time. Okay, so that's all for basically for today's content.